Hello, I am Prakash Saivasan. I would like to present to you about verifying reachability for TSO programs with dynamic thread creation. This presentation, uh, this work is joint work with Parosh Abdulla, Faouzi Atig, Ahmed Bouajjani, and Narayan Kumar. So what are the kinds of programs that we are interested in verifying? We are interested in verifying something called concurrent programs. What are these concurrent programs? These concurrent programs are some set of programs that have some set of shared variables, and they can communicate to each other using this shared memory, shared variables. So they can essentially read or write to these shared variables. In addition, we are also interested in another extra instruction that this process can perform, that is, it can create new threads. So we, in addition to the fixed number of processes that can read and write from the shared memory, each process can now additionally have an instruction which can create new threads. Now we are interested in verifying such programs. So let's come to the in weak memory model called TSO. We'll come to this in a minute. So if you take traditional architecture and if you run your programs, if you write to memory location, the write goes and sits in this memory location. If you read from a memory location, it reads from the memory location. So essentially, the operations are somehow atomic. But if you take modern architectures, because there is need for faster executions of these processes, the instructions are reordered. So what do we? So how does this reordering happen? It could happen in two ways. Either the compiler, because of optimization, can reorder this instruction, or there can be hardware support for such reorderings. And we are particularly interested in one such hardware support, which is due to Intel x86 architecture. So Intel x86 architecture allows a memory model called total store order or TSO architecture. So in TSO architecture, whenever you execute a process, when you execute a set of processes that happen to communicate with each other using shared variable or shared memory, so each of these processes is given a store buffer. And any of the writes that these processes perform are stored in the stored buffer, and any reads happen either from the stored buffer or from the shared memory. So before I go into a little more detail, I would like to say that writes are the slower instructions and reads are somehow the faster instructions. So the writes are stored or buffered, and the reads are allowed to happen faster. And the writes are updated at a much slower rate than the read operation. So essentially you are not blocking the reads because the writes have not happened. So this is the idea of these relaxed memory model or weak memory model. And I mean, we would like to verify the programs that run under these relaxed memory models, and in particular, we would like to verify it under the total store total store architecture. So, as I said, in this total store architecture, we have this store buffer that is provided for each process, and writes are buffered into this store buffer. So, each executing thread has a store buffer. These writes are buffered into the store buffer. And the reads can either happen from this buffer, that is, if a particular variable is, for suppose the process P2 wants to read X3 and X3 is available in its buffer, then the last write to the buffer is read. Otherwise, it is read from the main memory. So this is roughly the semantics of total store order. But remember, we have only said about reads and writes. We have not talked anything about create thread transition that the process can execute. Yes, and yes, the so remember we have this write stored into the stored buffer. They can be non-deterministically picked from the stored buffer and updated into the shared memory. So I will just rerun the animation for you. So you have x23 in P2, and this x23 can be deleted from this buffer, and it can be updated to the shared memory. Now, of course, as I said, we have not talked about thread creation. So what can happen when we have thread creation? Now, of course, there are various possibilities, but we look at one possibility and what is the problem with this possibility. So suppose P3 wants to execute a create thread instruction, and it creates a new process, but what can be the store buffer of this new process that is created? So let's assume that we allow this thread create semantics to create a new thread with empty store buffer. Unfortunately, this will violate causality. So what causality does it violate? So P4 can directly write to the main memory before all the writes of P3 are updated. So essentially, what you are having is that writes overtake other writes. For instance, P4 can write X3, which was already present in P3 and which has not been updated. So there is a causal, it violates causality between the write X3 of P4 and X3 write of P3. Similarly, reads can happen out of order. So what can happen? So you already have a write to X3 sitting in P3's buffer, which was actually executed before P4. We know that it was executed before P4 because P4 was created after that. But P4 was able to read directly from the main memory and not read the value that was provided or that was sitting in P3's buffer. So this is the problem. This violates causality, which many programming language disallows. So we came up with a different semantics for thread creation in the TSO semantics. So what is the semantics that we consider in this work? So we consider something called a hierarchical TSO buffer. So each time a process creates a new thread, two new TSO buffers are created. So how does this happen? So suppose P1 created P3, then we create two new buffers, P1 and P3, and we make P1 the creating TSO buffer as the parent of P1 and P3. Similarly, suppose P2, there was a thread P2, and P2 created, say, P4. Then we create two new buffers, P2 and P4, and make P2, the parent P2 buffer, the parent of P2 and P4. So every time we fork from the leaf buffer in this tree. So for instance, we can have some such tree or forest. And whenever a process wants to write, it always writes to the leaf buffer. And whenever it wants to read, it consolidates all the ancestor buffers and tries to read a value from this concatenated ancestor buffers. And we saw what happens when thread create happens. So thread create just forks the leaf buffer of this thread and creates two new child buffers. Of course, in our work we do not implement our TSO buffers as this dangerous looking forest or tree, but instead we duplicate the ancestors and we allow for each thread to have at most one buffer. So how do we do this? So suppose you look at this P1, P1, P1. We have a P1, 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 and we have this P5, P1, P1. So this P1, P1 is duplicated here, and we have a P1, P5 sitting on top of it. So we duplicate the ancestor buffers adequately, and we have enough duplicates so that each process works on a single buffer. And writes and reads are as usual. So write appends to the to its buffer. So each process has a buffer, so it appends to its buffer. Read reads from its buffer again. But updates are handled a bit more carefully. So whenever we update, all the duplicates. So if you look at this P1 in this hierarchical buffer system, we have one P1, whereas we have many P1s here. We have three P1s here. So any value that is updated from this P1 is also removed from the other P1. So this amounts to removing P1 from this single ancestor buffer. So we will look at this semantics a bit more carefully. So we have this causality preserving semantics. We will look at the transition system. So transition system has set of configurations. So what are these configurations in our setting? It has some set of processes. Then it has some set of states. Each process has a state. Each process also has a buffer. Okay, my slides has a bug. So this is a mapping from P to this tuple. So this is a variable, this is the value, and we also tag it with what process wrote this value. We'll come to this in a minute. But our configuration has set of processes. It has some set of, there is a mapping which maps each process to a state. There is a mapping which maps each process to a buffer, and there is a main memory. So this is our configuration. And how does our transition relation look like? So we will not go over all the transitions, but we will look at some important transitions in our transition system. So we have this write transition. What does this do? So whenever you want to write something, we just append that write into the buffer. But notice here, we are appending it in such a way that we have also identified who wrote this write. So we tag the write with the originator of that write. And this will be useful when we are doing the updates. Okay, what happens when we create? If you remember, we only had to duplicate the buffer when we create. So this is what we do. So when we create, we look at the buffer. So we look at suppose P is the one that is creating. So P is the thread that is creating this new thread, and R is the thread that is newly created. Then we just duplicate the buffer of P to R. And what happens when update? This is the most interesting part. So during an update, we look at all the buffers and look at all the values that, suppose we want to remove XPP from this buffer of P. We also look at all other buffers and see whether XPP is present in that buffer, and we simultaneously remove XPP from all the buffers. And this is possible because we have tagged each write with an identity. And whenever a duplicate happens, whenever we copy a buffer to another buffer, this identity remains the same. So now we can somehow simultaneously remove the duplicated value from all the buffers. Here, I'm missing some details here, but we will maintain as an invariant that whenever this XPP is in the tail end of the BP buffer, all its duplicates are also in the tail end of their respective buffers. And so we can successfully do an update. So this is the semantics that we work with. This is the new TSO semantics with the create instruction, support for this create instruction. And we want to now decide reachability on such systems. Reachability on specifically the TSO semantics with this new thread creation support. And we will look at the theory of well-structured transition systems. So what are these well-structured transition systems? It has a transition system, that is, it has some set of configurations, it has some set of initial configuration, it has some moves between the configuration, it has a move relation, for instance, or a transition relation between the configuration. In addition, it also has an ordering. It has a well-Quasi ordering. So well-Quasi ordering is reflexive and transitive ordering over the set of configurations of the transition system. And it also has its transition relation has this monotonicity property. So what is this monotonicity property? It says that if gamma 1 goes to gamma 2 and gamma 3 is a bigger configuration than gamma 1, bigger in terms of the ordering that we have, then there is also a gamma 4 which is bigger than gamma 2 and gamma 3 goes to gamma 4. So here, so gamma 1 goes to gamma 2, gamma 3 is a bigger configuration. So if our transition system, transition relation respects monotonicity, then this gamma 3 will go to gamma 4, which is bigger than gamma 2. So informally or roughly saying, what we are saying is, if you can do something from a smaller configuration, you can also do it from a bigger configuration. This is what monotonicity says. And there is a very famous and very nice result about this well-structured transition system, which says that give me a well-structured transition system, and if you give me a upward closed set U, then reachability from the initial set of states is decidable for such systems, provided we can decide some properties, or it has some nice properties. So what are these properties? That the ordering is decidable. Suppose I give you gamma 1 and gamma 2. Gamma 1 less than or equal to gamma 2 is decidable. And you can compute min pre. So what is min pre? It says that you give me an upward closed set, I can finitely abstract the pre of this upward closed set. So this is what min pre is, definition of min pre is, and the theorem asks for whether min pre is computable or not. So if you have these nice properties of, if you have a well-structured transition system, and if you have these nice properties, then this theorem guarantees reachability for such systems. So unfortunately, the TSO semantics that we described, don't have monotonicity. So we would like to come up with a different semantics that has this monotonicity property, and so that we can use this nice theorem to decide it to make it possible. And so you could take a classical TSO system, TSO semantic. It has something called a load buffer. So what is this load buffer semantics? So we will first describe the load buffer semantics for the classical TSO system, and we will show in our work we have extended this load buffer semantics for thread create instruction. We support it for thread create. We give support for this thread create instruction, and we will see what exactly is the how exactly we give this support. So what is this traditional load buffer semantics? If I have to say it informally, then what it means is, so if you take a store buffer semantics, TSO store buffer semantics that we saw earlier, every read is buffered, every write is buffered, and the reads somehow happen instantaneously. So the read either reads directly from main memory or it reads from the buffer if the value is available. Whereas in load buffer semantics, the writes are instantaneous. So every time you write, you directly go and write to the main memory, and the main memory is stored in the load buffer for the reads to read. So let us look at so what happens here. So whenever a write happens, the write is updated to the main memory immediately, and the main memory, the resulting changed main memory is inserted into the load buffer so that the later reads can be satisfied. And reads, now of course, reads from the load buffer and not directly from the main memory. So this is roughly the load buffer semantics. So we inserted support for this thread create instruction. So what do? Whenever a thread create happens, we simply duplicate the parent load buffer as the child load buffer and continue our operation. So this is the load buffer semantics that we propose, and we show in our paper that it is equivalent to the TSO store buffer semantics for thread create that we considered earlier. Here already you can see there is something magical going on. That in the TSO store buffer, we had we had the updates that were synchronous in some sense. So we had to update, we had to identify all the duplicates and update it simultaneously in the stored buffer semantics. Surprisingly, in the load buffer semantics, we don't have to do this because the writes are instantaneous here. So, and only the values of memories are updated to the load buffer, into the load buffer. So here, the requirement of simultaneous updation disappears. And in our paper, we have shown that with respect to reachability, the TSO store buffer semantics and the load buffer semantics with this create support are equivalent. So let us look at this load buffer semantics slightly more carefully. So what happens whenever we write, we update, first of all, update the main memory, and we also update the load buffer with the updated memory value. So we also tag this memory with what variable was written into this memory, and we also say whether it is a self-read. So self-read means it was written by that particular process. So for P, the P that P is a process that performed this, right? For that guy, we say that it is actually your read. And for other guys, we say that, okay, it is not your read, it is somebody else has written it. So odd means, odd essentially says that it is an ordinary memory, which means that somebody else has written this memory. And SRD means self-read, which means that you have written this memory. So suppose you want to create, what happens now? The create just duplicates the parent. So P is the buffer, P is the process that created the new process R. So R gets the copy of the buffer, load buffer of P. Delete is again simple. It just removes a value from the head of the buffer. Self-reads, if there is a self-read available in load buffer, then it is read. If not, then another read is read from the top of the buffer. So this is the semantics of load buffer. And in what we show in our paper is that this whole load buffer is not only well-structured transition system, but it also has these nice properties that the theorem required. And because it has these nice properties, that is, it has the ordering is decidable, min tree is computable, and it is actually, I mean, we define a well-quasi ordering over the configurations of this load buffer transition system, and we show that this its transition relation is actually monotonic. And since it has all these, it is a well-structured transition system, and it has all these nice properties, we can decide. We show that reachability. We can use the well-structured transition systems theorem and show that reachability on such TSO with load buffer semantics is decidable. And because we have also shown the equivalence of this load buffer semantics with the TSO store buffer semantics that we defined earlier, we also get that reachability on TSO with thread creation is decidable. So this is what we have done in the paper. We urge the viewer to look at our paper for more details. And I should have thanked you in the beginning of the talk, but thank you very much for showing interest in our paper, and thanks.